This is part two of my lecture notes for mechanical equilibrium. We have two problems to work that will be used to um, apply the concepts of mechanical equilibrium to two difficult or more challenging problems. I have a uniform ladder of 10 meters long and it weighs 50 newtons. It's resting against a frictionless vertical wall as in the figure. If the ladder is just on the verge of slipping, when it makes contact with the ground at 50 degrees above the ground, find the coefficient of static friction between the ladder and the ground. So here's a problem. Sketch the problem. Someone's already provided us a sketch. Draw all the forces. So we were told the ladder's 10 meters long. That's labeled. We were told that the ladder has a weight of 50 newtons. So the weight is equal to the force of gravity, which is equal to 50 newtons. Where does force of gravity act on this ladder? It acts right smack dab in the center of the ladder because they told us that the ladder was a uniform ladder. So it has uniform density. So the center of mass, center of gravity is located in the middle. They told us that the angle of with the ground is 50 degrees. They told us that this surface here is frictionless. So um, again, I'm in the process of drawing all my forces on the ladder. The ladder is in contact with that wall up top. That is, therefore, a force normal, and it's going to be from the wall. Now, force normal is perpendicular. I know it looks weird, but the force normal from the wall is perpendicular acts on the ladder, perpendicular to that surface. And so there you go. Now let's look at the bottom of the ladder. These are all the forces acting on the ladder. The ladder is in contact with the ground, and so there is a force normal from the ground acting upwards. And again, that's perpendicular to the ground. Now the ladder wants to slip and move to the left, but because there's static friction between the ladder and the ground, there is a force from static friction that is going to be opposing motion and parallel to the surface, so you'll see that it's parallel to the ground. They tell me that it's just about to slip, so we know that this is the max static friction. So let's refresh our memory. When force of static friction is at its max, it is equal to force normal times coefficient of static friction. Now, which force normal? Well, it's related to the ground and the ladder's material, so we are going to use force normal of the ground. Why would we use force normal from the wall? There was no friction at that point, okay? The first thing I'm going to do is they've asked me to find mu sub s equals question mark. So I'm going to start by setting up my three equations. Let's sum the forces in the x direction. All of them should equal zero. This object is in mechanical equilibrium, no acceleration. So I have two forces in the x direction. I have force of static friction max equals force normal from the wall. Okay, great. I've been asked to find mu sub s, so I'm going to go ahead and plug in mu sub s, force normal from the ground, is equal to force normal from the wall. I'm close. Mu sub s is equal to force normal from the wall divided by force normal from the ground. I just need to know those two forces and I can find mu sub s. Well, let's go find what we can find if we go to our next equation. We know that the sum of all the forces in the y direction must equal zero, and I have only two forces in the y direction. One pointing upwards, which is force normal from the ground, and one pointing downwards, which is the weight of the ladder, which is 50 newtons. Those added up are equal to zero, so we have just found one of the things we need in order to find the coefficient of static friction. So force normal from the ground is 50 newtons. All right, still don't have force normal from the wall, so we've got to be able to find it using the next condition of mechanical equilibrium, which is the sum of all the torques must be equal to zero. We're going to have to select an axis of rotation. I don't know the value, the amount of static friction, and I don't know force. Well, I do know force normal from the ground, but I don't know static friction max because I don't know force. I don't know mu sub s. So I'm going to select this AOR because that eliminates those two forces from my torque equation. Force normal from the ground through that axis of rotation does not create a torque. Force of static friction max, since it goes right through the axis of rotation, does not create a torque. So this 50 newtons will create a torque in the clockwise direction. I'll call that torque 1, and that'll be negative. This force normal from the wall, I'll call that torque 2, wants to create a counterclockwise rotation, so that's positive. So I'll say torque 2 minus torque 1 must be equal to 0. Definition of torque is force times R times sine theta. Torque 2, which is positive, is the force normal from the wall. How far away from the axis of rotation is that? It's 10 meters. What is the angle? Sine of what? Sine theta. Theta is the angle between the F and R vector. So if we go over here and look at that, here's the R value coming in. Here's the F. So I need this angle in here. Okay. I don't know what I just did. So I need this angle right here. And hopefully you see, since this is 40, this is 50. How did I know that was 40? Because that is an interior right triangle. There's also, what is it, alternating interior angles. That's why that is theta. So it is 50 degrees. Okay. Subtract torque 1. Torque 1 is the torque caused by the weight of the ladder. That's 50 newtons. How far is that force away from the axis of the rotation? It's 5 meters times sine of some angle. So what angle is it? So hopefully you see that the R vector comes up here. Here's the force, so I need that interior angle right there. And that will be 40 degrees. Make sure your calculators, folks, are in degrees. That must be equal to 0. I have all my, the only unknown in this equation that I just set up was the force normal from the wall, which is the last piece of information that I must find in order to solve and answer the question. So if I rearrange that equation properly and plug that into my calculator properly, I will get 20.979 newtons. So I can go ahead and put 20.79 divided by, what did I say, 50, and I will find mu sub s to be equal to 0.42. Okay, take your time. 3 equations. You're going to have to use all of them in that problem. All right. Looks like I started this, but need to redo. Okay, we're going to do one more. And it's why I chose this problem is to teach you about a hinge. Okay, determine the force of the tension Ft in a cable that is supporting a uniform beam, so the mass is distributed evenly. The beam is 10 meters long, has a weight of 6,000 newtons, and attached to the wall by an ideal hinge as shown in the figure. The cable is also attached to the wall and makes a 40-degree angle to the beam. I'm just going to expand this for a minute and talk about this hinge. So here's my hinge and my beam that connects. I want to talk about the forces that a hinge has. If you can imagine, the weight of that bar, of that beam, is somewhat supported by the hinge. So there is a force upwards from the hinge in the y direction. In addition, the hinge has a force from the hinge in the x direction as the actual beam is kind of pushing on the bolt, and it's a normal force actually. So the actual force from the hinge is at some vector addition of those two forces. Okay, so that is the proper way to draw the force from the hinge. It's at some angle, unknown, because you don't know the magnitudes of those two. You'd actually have to find it. Sometimes I have seen a problem on the AP exam where they ask for the vertical force that the hinge is putting on an object. So you must be able to draw them. And sometimes we don't need to break them up. You'll see in just a minute. So I've got a force downward. That's the mass. I'm sorry, that's the weight of the beam. So force of gravity acts on that beam and puts a force downward on that beam of 6,000 newtons. And then I have a force of tension upwards at the angle shown. So those are my three forces. Let's see if we can solve it using only that. Okay. They want to know force of tension. So one nice thing about summing the torques is that I don't really have to break my forces up into components. So I'm going to try to solve for force of tension using no components at this time. I'm going to use axis of rotation. I'm going to select that at the hinge since I don't know anything about that force that the hinge is putting on the beam. And now I've eliminated it from the sum of the torque equations. Now this 6,000 newtons, I'll call that torque 1, is going to create a counterclockwise rotation, and so that'll be a negative torque. This force of tension, I'll call that torque 2, is going to try to rotate counterclockwise, so it'll be positive. So the sum of all the torques is equal to 0. So I will say torque 2 minus torque 1 equals 0. Definition of torque is force. Torque is equal to force times distance away from axis of rotation times sine of the angle between the force and the displacement or distance vector r. Okay, so T2 is force of tension. That's what I'm trying to find. Let me go down here. Force of tension, there's the force. I don't know it. How far away is this force of tension from the axis of rotation that I have chosen? Well, they told me the beam was 10 meters long. Here it is right here, so I know that. And then I have sine of some angle. The angle is actually the 40 degrees. That is the angle between that r vector and the force of tension vector. Then I'm going to subtract the torque caused by the weight of the beam. So the weight is 6,000 newtons. That's the force of gravity acting on the beam at that location. Where is that located? It's right smack dab in the middle because they said it was a uniform beam. So that's going to be 5 meters away from the axis of rotation that I have selected. And then hopefully you see that this angle is 90 degrees. This angle right here is 90 degrees. So sine of 90 is 1, and I'll just leave that off. So I don't actually need to break my components, my tension and my force or my force of the hinge into its components to solve this part of the problem. I can rearrange that equation, make sure your calculator is in degree mode, and I will get force of tension is equal to 6,000 times 5 meters, so that's a Newton in there, divided by sine of 40 degrees, and then 10 meters on the bottom. And I'll get left with a Newton, and I'll find force of tension to be equal to 4,667 newtons, unless I did something wrong. All right, now, next question. Determine both the horizontal and vertical forces acting on the beam at the hinge and the resultant force from the hinge. So now I do need to break up my components, my forces into components. I'm going to redraw it. So I have force of the hinge in the y direction. I have force of the hinge in the x direction. I have force of gravity, which is the weight, which is 6,000. I have force of tension in the y direction, which will be force of tension, that's opposite of 40, so that'll be Ft sine theta. And then I have a piece of that force of tension in the x direction, so that's force of tension in the x, that's adjacent to that angle that was given, so that'll be force of tension times cosine theta. So now we actually know the force of tension, so we can calculate the components of, force of tension in the x and y are known quantities. So in order to solve this, I actually have to, again, use one of my other conditions of equilibrium. The sum of the forces in the x direction are 0. How many forces do I have in the x direction? I have 2. The force of the hinge in the x direction minus the force of tension in the x direction is equal to 0. So the force from the hinge in the x direction is equal to the force from the tension in the x direction, which is Ft cosine theta, which is the value that we found, which is 4,667 newtons times cosine of the angle, 40 degrees, which will give me 3,575 newtons for the force of the hinge in the x direction. I will sum the forces in the y direction. They must add up to 0. How many forces do I have in the y direction? I have 3. I have 2 positive, 1 negative. Force of the hinge in the y plus force of tension in the y minus the weight of the beam is equal to 0. I'm trying to find the force of the hinge in the y direction, so it will be equal to the weight of the beam minus Ft sine theta, which is equal to 6,000 minus 4,667 newtons times sine of 40 degrees. If you plug that into your calculator, and assuming I did this properly, I get 3,000 newtons. That answered a few different parts of that. That's force of the hinge in the x. This is force of the hinge in the y. Now, what is the resultant force of the hinge? Well, I have to draw those tip to tail. So here's my x and here's my y. This is 3,000 newtons. This is 3,575 newtons. And I will use Pythagorean theorem to find the actual force of the hinge. I haven't done that. So we know that force of the hinge squared is equal to 3,000 squared plus 3,575 squared. And then we'll add those together and take the square root. Let me do that quick. Oops, clear. 3,000. 3,575 squared. Okay, I got the force of the hinge is equal to 4,666.9. So I'll say we'll say 3 sig figs. We'll just call that 3 sig figs. That's usually what they ask for. There we go. There's 3 sig figs, but that doesn't tell me the angle. So I'm going to find that angle, and theta will be equal to the inverse tangent of the opposite, 3,575 divided by 3,000. And so that will be, sorry, I didn't have that pre-calculated yet, 3,575 divided by, I got 49.99, so I'll call it 50 degrees. Okay, there is technically at 50 degrees above beam. That is the force from the hinge acting on the beam. All right, that concludes my lecture video for today, and it concludes my notes on equilibrium. Now we need to practice.